This board passed every DRC check, clean report, 0 errors. It still failed at 5 gigabits. The defects that kill SerDes links hide where DRC never looks, in the electromagnetics of the vias, the reference planes, and the coupled traces. In the next 10 minutes, I will show you how to catch every one of them. In seconds, not simulation hours, using electrical rule checking in SimBure. Let's start. You will run a complete post-layout sign-off on a real board in 3-stage passes. Pass 1 is electrical rule checking, reference integrity, impedance continuity, and crosstalk discovery, fast enough to screen thousands of links. Pass 2, fast signal integrity, crosstalk and traces, delay and skew, and a first look at losses. Pass 3, 3DSI, full-wave electromagnetic validation of the riskiest structures, vias, and BGA breakouts. And it all hangs on one rule: pass each level before you spend compute on the next. ERC is model-based defect checking. It simulates the actual signal link. It verifies reference integrity. Are your reference conductors under control? And are the vias localized? It checks impedance continuity along traces and through vias. And it flags where a crosstalk may come from. Under the hood, a 2D field solver plus fast electromagnetic via models. That means a link checked in a fraction of a second, or thousands of links with automation. And you move to FSI only when every critical issue is resolved. Let's get started. Open SimBure and create a new solution. The solution is built around the standard you are validating. Here, that's QSGMII, running at 5 gigabits per second. Rise time, 30 picoseconds. Measure 20 to 80%. Create the solution for 5 gigabits per second, and the 30 picosecond rise time comes in by default. From those numbers, SimBure sets the analysis bandwidth. It will run up to 14.4 GHz. Proceed with the solution and import a PCB layout. Two importer options, ODB++ or Allegro. Take ODB++. Select the design, an open compute project board, load the slightly corrected stackup along with it. Set the technology to package with PCB. Processing will take a bit longer. Click Import. The importer starts working through the board data. Here's a habit worth keeping. After every import, check the stackup. Close the compliance analyzer and verify the materials. This stackup was corrected to add solder mask. Make sure the solder mask dielectric is selected properly, just as in the board's description. Anything wrong? You fix it right here. For instance, add a roughness model for the conductors, specify it, make any other corrections, then export the corrected stackup. Next time, the stackup with roughness loads in one step. Now open the board view. The full layout renders. Your targets are the QSGMII links, and they run all over the board. Type QSGMII into the filter to pull them all up. You could select everything and run ERC on all of it, but not all of these nets are high speed, so pick out just the high speed ones. Hide all layers and show only the top. Now the links stand out. Put the cursor on a trace to confirm it. You will select 8 links and simulate them in parallel. Adjust visibility to see them better, then Control-click each one. Each selected pair highlights across the board. That's 8 links selected. Show the layers again. This selection keeps the analysis to 32 ports, and it runs on the SimBure Verify license. First pass. Electrical rule checking, tied to this exact data rate. Now the compliance conditions. Require 2 stitching vias per signal via. Check impedance against the 100 ohm spec and flag any crosstalk above 20 millivolts. These are microstrip structures with fairly generous spacing, but microstrip crosstalk can strike even at large spacing. So raise the coupling distance to 50 mils and check extract reference conductor for the 3D view. Click Run. Symbior's fast engine goes to work 1170 cross sections first. Solved by the SFS field solver, then the vias. Seconds later, it's done. The analysis completes and renders everything it collected, impedances and crosstalk. Crosstalk is evaluated along parallel line segments. Switch to the 3D view. 2 caveats. The excitation is a 1-volt step and the lines are treated as lossless, so real crosstalk will be smaller. Losses work in your favor. Now, the violations. See those bumpy roads? Discontinuities in the reference plane. To see them clearly, restrict the view to just the relevant layers. There they are, cutouts under the holes. Impedance, meanwhile, sits close to 50 ohms everywhere. That's the green on the scale. And these markers are the places crosstalk may come from. That's crosstalk discovery, where it may come from, and the maximum value to expect at that location. The exclamation signs flag via holes, click 1 for details, via impedance from top and bottom, at which frequency, and the localization frequency, 16 GHz here. This one has just a single stitching via. Observing is fine, but you need a report and a way to fix things. So, here's the report Symbior generates. Every via short on stitching vias is listed, but the severity is low, so they can stay. Reference discontinuities are a different story. Several locations are critical. Jump to one, this is the location. Some are marginally critical, some really critical. This one is real. Zoom in to make it obvious. The metal is cut out around the via and around the capacitors. A genuine discontinuity. Everything in the critical range gets fixed before any further analysis. No exceptions. Impedance next. Only a few discontinuities, and all low severity. Low severity warnings can clutter a report. You can switch off collecting them in the compliance analyzer. To create the report, click Save. Symbior writes up the whole run, including the low severity violations. Switch back to the 3D view. Low severity conditions can be checked off entirely. That's the skip violation checkbox, and it keeps the report short. The report lands in the solution directory. Open it, and there it is. All the boxes, with reference discontinuity the most critical. Each entry gives the locations and the instruction for the fix. That is ERC, the critical defects, caught in seconds. In part 2, we move to fast signal integrity, crosstalk, skew and losses, checked against the compliance masks. If you design high-speed boards, join the PCB Design Skool. The link is below.